Hey everyone, today we're going to just do a little review of the intro that we did in class the other day, and we're going to go a little bit deeper into this idea of arithmetic and geometric sequences, just to see if we can get some explicit formulas for these and make our lives a little bit easier when we're dealing with these things. So we're going to start out just talking about arithmetic sequences. We talked about these the other day. So remember, this is where you have a common difference. So every arithmetic sequence has a common difference. That means that you're adding or subtracting the same number every time. And the letter we usually use for the common difference is D. So just a really quick example. Remember, we're always going to have the first term. So first term will be A1. We always use A for arithmetic sequences, so you might call this AN. Arithmetic sequence AN. So first term is A1, and it has this common difference D. So a quick example of what you might have for an arithmetic sequence. Maybe you would have something like -3, 1, 5, 9, and that would keep going. Okay. So in this case, we just have to figure out what's our first term. Well, that's not too bad. Our first term is -3. It's just right here. And our common difference, D, well, what are we adding every time here? Looks like we're adding 4 each time. So that's our common difference. And that's all you have to be able to find the formulas we're going to talk about today. So we have our first term and our common difference, D, and that's all you need. Let's do another one. What if you had a sequence that was -7, -9, -11, -13, keeps going. Looks like our first term this time is -7. And our common difference D, well, let's see here. We're subtracting 2 every time, so our D is -2. That's all there is to it. So the first kind of formula we talked about was called recursive. So a recursive formula, remember this is the one where it depends on the prior term. So the recursive formula looks like this every time for an arithmetic sequence. You're given A1, and we'll have to put in the A1 there. So like for this first sequence up here, maybe if I put in our A1 is -3. So that'll be different for each sequence. And then we have to have some way of getting AN that's based on the prior term. So the prior term, what we use there is AN minus 1. And then I'm going to add the D to that each time. So all I'm doing is looking at the previous term, then I'm adding D. So in this case, to get any term, AN would just be the prior term. And it looks like we're adding 4 every time. So it would just be +4. And that is your recursive formula for that sequence. That's all there is to it. If you want to try the recursive formula for this one, you could pause the video real quick and give it a shot. All right. So let's see if we can do it together now. So if we have our first term is -7, and then our nth term would just be AN minus 1. So that's the prior term. So if we're trying to find like A3 right here, I would look at A2. And then what do I have to do? I have to subtract 2. Now some of you say, wait, hold on a minute. I thought we were adding D. Well, yeah, but our D is -2. So you could think about this as AN minus 1 plus -2. But usually that isn't how we write it. We just write -2. All right. So one thing that we talked about yesterday that we kind of cheated on, we said you could start it at 0 or at 1. So you could start at A0 or you could start it at A1. We're kind of going to forget about the A0 from now on. We kind of cheated yesterday. Today we're going to focus on always starting our first term at number 1, because then we'll just have a uniform way of dealing with it. So let's talk about an explicit formula. Remember, recursive formula is nice if you have the prior term. Explicit is just like if I want to find A like 500. Well, with a recursive, you would have to know 499. So let's talk about how we can get an explicit formula. So I'm going to kind of steal this formula that we have up here. So we have -3, 1, and 5, 9, etc., etc. So we always have this first term, A1, and that's just going to be whatever the heck that is. Then to get A2, it's going to be A1, and then we're going to add the difference D. So in that case, it was 4. And then A3 will be A1 plus D. That's our prior term. And then we would add D again. Let's see if this is working. So we take our first term and add 4. We get to 1, right, because our common difference here was 4. And then if I add 4, that gets me to 1. And then 4 again gets me to 5. And then A4 would be A1 plus D plus D plus D again. So we just keep adding one more D every time. Let's see if we can get a formula going for this. So the first one's just A1. The next one is A1 plus D. Next one is A1 plus D times 2, right? Because I have two D's there. So you add D and you add D again. Third one is A1 plus D times, looks like 1, 2, 3. And look at this. The first term has no d's, second term has 1d, third term has 2d's, fourth term has 3d's. It looks like every term, if I am on the nth term, so an, it looks like a formula for that would be a1, because all of these have an a1 involved, and then it would be plus our difference, not times n, right? It looks like it's 1 less than n, so I'm going to write that as n minus 1. And this right here is going to be our explicit formula for arithmetic sequences. It's that easy, okay? So explicit formula, got too excited about the formula there. So explicit formula for arithmetic looks like this. The nth term, an, is going to be a1 plus d times n minus 1. Okay, that's an important formula. You're definitely going to want to write that down. So what this means is if I want to find a500, and I know our first term, like we have right here, is negative 3, plus our difference, which is 4, and then I'll just multiply by 500 minus 1. Well, 500 minus 1 is 499 times 4. I'm going to have to do some math in my head here. Probably grab a calculator for this, but 500 times 4 is 2,000, but I don't need that last 4, so it's going to be, what is that, 1996. I mean, negative 3 plus 1,996. So it looks like that's going to be 1,993. So we did not have to go through 500 terms to find that. That's the nice thing about an explicit formula. And it's not that bad at all. Now, where this comes from, this is kind of cool. If you move this a1 to the other side, you have an minus a1 is equal to d times n minus 1. Now, this may look like a formula that we've seen before. Do you guys remember point-slope form of a line? It looks like y minus y1 equals m times x minus x1. We might have used b's and a's in here, I don't remember. But this was when the point x1, y1 is on the line. And then you just want it for a general y and x, and then the slope was m. If you remember in class the other day, we actually graphed some of these arithmetic sequences, and they made lines. Remember we had dots like this? And we said, well, the slope is the d. That's why the d is right here is the slope. And then you can choose any point on there that's n comma an and 1 comma a1, and this is going to work out, which is kind of cool. I think we're going to try an example now. So in this example, we're given a2, it's 12, and a6 is 4, and we want to find an explicit formula for an and a recursive formula for an. So let's just kind of take what we know here, because I'm not really sure how to attack this problem. So we know our explicit formula is an equals a1 plus d times n minus 1. And they give us some information here. So they tell us that a2 is 12. So I'm just going to plug that into my formula. a2, so it looks like my n is 2. I don't know a1, and I don't know d. But if n is 2, I've got to put a 2 right here. So 2 minus 1. So all I did was I plugged in what I knew. I knew that a2 is equal to a1 plus d times 2 minus 1. But a2 is 12. So my first formula here is 12 is equal to a1 plus d times 2 minus 1, which is just 1. Now, let's see what I can do with the other one. I have a6 is equal to, well, that would just be a1 plus d times 6 minus 1. Put that in numbers. a6 is 4. So we have 4 is equal to a1 plus d times 5. Now, it would be nice if I could find a1 and d. So if I can find a1 and d, I can just plug them into here, and I'll have my explicit formula. Well, we have these two unknowns and two equations. It's called a system. Right? We can use this system and we can solve it to try to figure out what a1 and d are. So what I'm going to do is I'm going to write this guy on top. So I'm going to have 4 is equal to a1 plus 5d. I'm going to put the 5 in the front. That's fine because multiplication is commutative. Then I'll write underneath it 12 is equal to a1 plus d. Right? Just d times 1. So this is a system. I'm just going to subtract these equations. 4 minus 12 is negative 8. The a1's cancel. That's why I chose to subtract. 5d minus d is 4d. Now when I divide both sides by 4, I find out that d is negative 2. That kind of makes sense. You might have been able to figure that out just by looking here. If you start with 12 and you're getting to 4 in 4 terms, so you're kind of thinking I have 12, that's a2, so I have a3, a4, a5, and then a6 is 4. To get from 12 to 4 in that many steps, looks like if you subtract 2, you get to 10, and then 8, and then 6, and then 4. So you might have figured that out without doing all this math. But sometimes, like in the book, there was one problem where the d was like 2.7, and if that's the case, it's going to be really hard to figure out how many times you jumped or what the common difference is. So easier to be able to use this system form. So I know d now is negative 2. Now I have to find a1. I can choose either one of these to use. I think I'm going to choose this one. So I have 12 is equal to a1 plus negative 2. We'll add 2 to both sides. Looks like a1 is 14, which makes sense. If a2 is 12, then the first term should have been 14. So our explicit formula is just going to be an is equal to 14 minus 2, right? I could put plus negative 2. I'm just going to put minus 2 times n minus 1. And now I have a way of finding any term, right? The nth term or any term. It's a bad math teacher joke. Any term. Yay. Okay. Now, a recursive formula, that's easy. I have a1. Just found it. It's 14. And then our an is going to be the an minus 1. And then I have to add my common difference, which we found out was negative 2. So I could do minus 2 or plus negative 2. I think I'm going to do minus 2. And that's our recursive formula. Cool. All right, just a word problem here. So Mr. Fransky's got some problems, which is we all know is true, but let's just see what this one's about. So Mr. Fransky wants to solve 2 math problems this week. Okay, that means our first week, A1, is 2. And he wants to solve an additional 3 math problems every week for the rest of his life. Oh, well, that sounds like fun. So an additional 3 math problems every week. So A2 would be 5. A3 would be 8. And this is going to keep going. So first question we pretty much already answered. How many math problems will he solve in week 2? 5. We're going to write a recursive formula. So let's see here. It looks like our first term is 2. And our nth term would be an minus 1. Plus, how much are we adding each time? Well, he wants to do 3 more problems every week, so it's 3. That's it. Explicit, same thing. If you can find a1 and d, you have everything. So explicit formula, an is always equal to a1, which in this case is 2, plus our common difference, 3, multiplied by n minus 1. That's it. So we have our explicit and our recursive. What week will Fransky first solve more than 100 problems? Well, what that means is I want to know an is greater than 100. So what I'm going to say is, well, when does he hit 100? I don't think it'll be an exact number, but it'll get us close. So when will you first solve more than 100 problems? You could just start plugging in values for n. You could try like 20, maybe 25, I don't know, and keep trying values until you get it over 100. But I'm going to try to be smart about this. So I'm going to do 100 is equal to 2 plus 3 times n minus 1. I'm going to figure out what n value will make him solve 100 problems. So if I subtract 2, I get 98 is equal to, I'll distribute the 3, 3n minus 3. If you add 3 to both sides, you get 101 equals 3n. Now you can grab a calculator here. If you do 101 divided by 3, what you're going to get is n equals, so we're going to divide both sides by 3. So 101 over 3, which is 33.6 repeated. And when you get this number, it's like, well, that doesn't seem like it makes very much sense. So the problem is, though, at 33 weeks, if you put 33 in for n, you get 32 times 3, which is 96, plus 2 is 98. That's not quite 100. So you need to go just a little bit more. So he'll have to do in his 34th week. And you can check right here. 34 minus 1 is 33, times 3 is 99, plus 2, 101. So that's the first week that he'll be solving more than 100 problems. Cool. Oh, I had an extra slide for that. Okay, so that's going to kind of put arithmetic sequences down. Let's take a look at geometric sequences, which are, I think, a little bit easier even than arithmetic, because the formulas just make more sense to me. So, a geometric sequence, this guy has the first term, g1. That's our first term. And the difference between a geometric and an arithmetic sequence is that this one, instead of adding every time, you're going to be multiplying every time. So we have a common ratio instead of a difference. So we have a common ratio, and we use the letter r for that. Very creative here. D for difference, r for ratio. So that means we're multiplying every time. For example, try to do a simple one here. We could have like 4, 12, whoop, that's a 2, I promise, 36, make that better. So 4, 12, 36, 108, and that keeps going. So in this case, our first term, G1 is 4, and our common ratio, well, let's see here. If you divide 12 by 4, you get 3. 36 divided by 12 is 3. 108 divided by 36, they're all 3. So not too bad there. Another one could be maybe 64, and then 16, 4, 1, 1/4, and that keeps going. In this case, our first term is 64. And it looks like what we're doing every time, if you do 16 divided by 64, or 4 divided by 16, 1 divided by 4, every time we're multiplying by 1/4, right? Because you take a fourth of 64 to get 16, etc., etc. So if we were to do this in recursive formulas, recursive formula for this guy, G1 equals 4. To get the nth term, I'm going to take the previous term, Gn minus 1, and I'm going to multiply by 3. Okay, you can use parentheses. You don't really have to. You could do a dot, whatever you want. For this guy, we have G1 is 64, and our nth term will be Gn minus 1, multiply, use a dot this time, by 1/4. Again, not really useful if we don't have an explicit formula, because this we would have to have the previous term to get any term. So the explicit formula for geometric sequences is not bad at all. If we think about this, I'm going to steal this guy right here, the 4, 12, 36, 108. So we have 4, 12, 36, 108. So if we look at a geometric sequence, we think about G1, G2, G3, G4. The first term is just going to be G1, in this case 4. The second term, I'm going to take G1, I'm going to multiply by R. So this case would be 4 times 12, or sorry, 4 times 3, which gives us 12. Then the next one I'll multiply by 3 again. So I'd start with G1, and I've multiplied by R, that's G2, and then I multiply by R again. Next one, G1 times R times R times R. And that's going to keep going. Let's see if we can get a formula for the nth term. This looks a lot like when we did this with the A's. Let's go back to that slide. It's right here. Nope, one more. So we had A1, but this time we were adding. We had 1D, and then 2Ds, and then 3Ds, but it was always 1 behind the N. Let's see if that's happening for the geometrics. One more. Well, here we have no R's, right? For the first term, we have no R's. Second term, we have 1 R. Third term, we have 2 R's. Fourth term, we have 3 R's. Once again, it's 1 less. We can write this a little bit differently. This is G1, G1R. This is G1R squared. G1R cubed, right? Because you're multiplying it 3 times. So it's always 1 less. So the nth term, Gn, will be G1 times R to the n minus 1 power. And that's our explicit formula. So explicit for geometric. Explicit formula for geometric is just Gn is equal to G1 times R to the n minus 1. Usually you see parentheses around that R. So let's see if it works. Let's see if we can get our, I don't know, our third term here by using our formula. So G3 should be G1 times R to the 3 minus 1. We know G1 is 4. Our ratio here we said was 3 every time. So 3 to the second. That would be 4 times 9, which is indeed 36. So it checks out. Third term is 36. Some money. Whenever you talk about geometric sequences and multiplication stuff like this, you're always going to end up talking about money. So let's see what's going on here. You're investing $10,000, and it's in a 5-year cash deposit with an annual yield of 4.83%. The amount you begin with and the amounts you have at the end of consecutive years form a finite geometric sequence. So we're doing a geometric sequence here. We must be multiplying by something every time. We want us to find an explicit and a recursive formula. So, not too bad to get G1. G1 is just how much money you start with. That's $10,000. Now the R, this throws people for a loop. We talked about this back when we did PE to the RT, all this stuff in Chapter 3 with money. But our common ratio here, it can't be just 4.83%. Well, for one reason, because 4.83 is a percent. If you multiplied by 4.83 every year, so if you got to $40,000 or almost $50,000 in your first year, that is definitely an account I would want to be in. But that's not how percentages work. So some people make the mistake of saying it's 0.0483. But if that was right, if it was 0.0483, if I multiply that by 10,000, do you see how you would have a lot less money in your second year? What we have to do is we have to say we're going to keep that 10,000 and we're going to gain an additional 4.83%. So you need a 1 out in front of there. That is going to keep the 10,000 and it's going to gain you an additional 4.83%. So kind of like with in arithmetic, you need to get D and the first term. Here we have to get R and the first term, and then we have everything. Explicit formula, we know Gn is just G1 times R to the n minus 1. So for this particular problem, it's going to be Gn is equal to 10,000 times 1.0483 raised to the n minus first power. And that's our formula. That's the explicit. Now let's do the recursive. G1, we know G1 is 10,000. And then Gn is just going to be the previous term, Gn minus 1 multiplied by R, 1.0483. That's all you have to do. That's our recursive formula. Not too bad at all. So, you can gain money on things. Unfortunately, my mathematical toys also can lose money on things. Oops. Huh. I forgot a slide. Huh. Well, let's see if I can remember it. Mr. Fransky has an abacus, and originally that abacus cost $100. But it depreciates. Depreciates means it loses value. It depreciates at 27% per year. And we just want to come up with an explicit and recursive. Explicit, recursive. And I think I also asked a couple other questions. We'll see if I come to mind as we're going through here. So it looks like our first term, G1, is 100. That's how much it's worth initially. Now our R here, it's not 27%. Depreciates means it loses 27% of its value. So what you want to think about, this is kind of similar to the, it wasn't 0.0483, it was 1.0483. How much is left? Well, if it depreciates 27%, 100 minus 27% is 73%. So R is 0.73. That's how much will be left each year. So I'll have 73%, so it'll be $73 the second year, and then 73% of that the third year, and every year you'll get 73% of your value. So explicit formula, Gn is 100 times 0.73 to the n minus 1, right? That's just from our explicit formula for geometric. Recursive, G1 is 100. Gn would be Gn minus 1 times 0.73. That's all there is to it. Now, I think I also asked the question, when will it be worth less than $5? Probably quickly. So only worth less than $5. Well, let's find out when it's equal to $5. If we do 5 is equal to 100 times 0.73 to the n minus 1. So if we divide by 100, 5 over 100 is 1 over 20, is equal to 0.73 to the n minus 1. Now, unfortunately, right now, we don't really have a way to solve for that n. We're going to learn about that in Chapter 9. So right now, what you would have to do is just start plugging in values and seeing what you get. So I might guess maybe try n equals 20. So after 20 years, let's see how much it's worth. So I put in n equals 20. I'm trying to see if this is going to be less than 5. So if we do 100 times 0.73 to the 19, that's 20 minus 1. So 0.73 to the 19th power, just using my calculator here, that's 100 times 0.0025. I think that's actually going to be too small already. So that's 25 cents. So that's too small. So 20 years was too long. Let's try 15 years. When n is 15, if we do 0.73 to the 14th times 100, let's see what we get. So you 0.73 to the 14th, just using my calculator here, and multiply by 100. So then with $1.22. So that's still too long. So let's try 10 years. Running out of space. So if we do 10 years, if we do 0.73 to the 9th power times 100, 0.73 to the 9th times 100. Ooh, we're getting close. That's 588. I bet one more year will do it. If I go to 11 years, so 11 years would be 100 times 0.73 to the 10th power. 0.73 to the 10th times 100. That's the first year for sure. That's $4.29. And we have a winner. So 11 years. 11 years, that's the first time it'll be less than $5. Remember, that's because this 10 came from n minus 1 over here. Cool. All right, so midway is not accurate. We don't have half of it left. We got through most of the stuff that we need to get through, but just a little summary chart here of all of the stuff we've talked about. So one thing that they do differently, they put the d at the end. I like it at the front. Doesn't matter too much though. And then they have the recurrence relation, so that's an minus 1 plus d. This is just a nice little summary chart of everything we've talked about. Common difference for arithmetic, common ratio for geometric. So if you want to pause this and make sure that you have all of this written down somewhere, it's nice to have kind of all in one place. All right, let's move on. Middle terms. So middle terms for arithmetic sequences, not too hard. So the 7th term, so let's say this is term 7, is 103. Here's the 8th term, here's the 9th term. The 9th term, they tell us, is 251. They want to say, what is that 8th term? Well, if it's arithmetic, we know the difference from 108 to the 8th term and the difference from 108 to the 9th term is going to be the same. So really, I'm looking for the middle of those two numbers. We know how to find a middle. We talked about it back in chapter 1. We just take the average. And the average is another word for it. It's called the arithmetic mean. You may have heard that. Arithmetic mean. So the arithmetic mean, you just add them together and divide by 2. So we do 108, plus 251, divide by 2. Grab a calculator if you need to. It's 177. So A8 is 177. So we need to find the middle term of things in an arithmetic sequence. You just take the average, and that's really easy. Geometric is a little bit trickier. So if I know the 8th term of a geometric series is 320, here's 9, here's 10. The 10th term is 5120. What is that 9th term? This is harder because it's not halfway in between, right? Think about like a simple geometric series, like 2 times 2 is 4 times 2 is 8. The differences here are not the same, right? It's much bigger gap on the right side. In fact, in this case, twice as big. But here I don't know what my ratio is, so I don't know how to find that number right there. So there's something called the geometric mean. Geometric mean. And I'll show you why it works in a second, but the geometric mean, if I know that x, y, z make a geometric sequence, then every time y will be the square root of x times z. And this is what is called the geometric mean. Okay, so geometric mean of two numbers, you multiply them together and you take the square root, and that's all there is to it. So this guy right here, this middle term is just going to be, so a9, or g9 in this case, is just going to be the square root of 320 multiplied by 5120. And that happens to be equal to 1280. And we can check. Is 1280 over 320? Let's see, I think that gives us 4. And 5120 over 1280 is also 4. So we see we have a common ratio if we put 1280 in that 9 spot. The reason this works is because if you think about what a geometric sequence is, we have 320, and then we would have 320 times r, whatever the common ratio is, and then 320 times r squared. If you multiply the outside terms, right, this guy is 5120, and when you do the geometric mean, that's the first thing you do is you multiply them. When you multiply those outside terms, you get 320 squared times r squared. If I want this middle term, which is 320r, I just take the square root. That gets rid of both of those squares. And that's how you find that middle term. Kind of cool. Geometric mean. That comes up occasionally on the ACT. Kind of good to know. Close to the end here. So just a few sequences here. We're trying to figure out if they're arithmetic, geometric, or neither. And if you want to write out the formulas for these, you can. I'm just going to say whether they're arithmetic or geometric, just looking at them. So this first one, 18 to 24, that's the difference of 6. 24 to 30 is a difference of 6. 30 to 36, also a difference of 6. Hey, this is arithmetic. So I'm just going to put an A there for arithmetic. A1 is 18. D is 6. So you could find our explicit and recursive formulas using those. Next one, we got Bn. 16, 12, that's a difference of -4. Ooh, but then we have -3, and then like a decimal. That doesn't look good. Let's see if it's geometric. So to check if it's geometric, I'm going to divide 12 by 16. 12 over 16, I can reduce that by dividing them both by 4. That's 3/4. Let's try the next one. 9 over 12. I can divide both of those by 3, also 3/4. Oh, this is looking good for geometric. The next one, if you do 6.75 divided by 9, you have to trust me on this one, or you can grab a calculator. It's also 3/4. So this is a geometric, and it looks like G1 is 16, and our common ratio is 3/4. The last one here, 1 to 3, that's a difference of 2. 3 to 6 is a difference of 3, so it's not arithmetic. 1 times 3 is 3, times 3 is 9, so it's also not geometric. So that one right there is neither. It's not arithmetic or geometric. And those neither ones, sometimes there's a pattern, and sometimes there isn't. So in this case, we have a situation where it's not arithmetic or geometric. If you subtract these, you would get a messy number, but it's not going to be the same for each one of these. And also, if you divide 4/25 by 1/5, that would give you, I think it would be 4/5. Yeah, because you have to multiply the top by 4, bottom by 5. But the next one would actually give you, let's see, if you divide those out, I think it would give you 45/4, which is not the same as 4/5. So this is a neither, but it looks like we have a pattern going. The bottom, we have 5, and then that's 5 squared, that's 5 cubed, that's 5 to the 4th. So we're just increasing with powers of 5. And on the top, we have 1, and then 4, 9, 16. These are special numbers. They're perfect squares. So you can still get a formula for this. The nth term, it looks like the top is just n squared, because 1 squared, and then 2 squared, 3 squared, 4 squared. And on the bottom, it looks like we have 5 to the n power. 5 to the first, 5 to the second, 5 to the third. So it's still possible to find a formula. You just kind of have to look at it, right? It's not arithmetic or geometric, but it still has a formula. Let's take a look at this one. Rn is the number of dots in a rectangular array of dots with n columns and n plus 1 rows. So let's think about what that's going to look like. R1. So R1 would have 1 column and 2 rows. So 1 column and 2 rows. So the total number of dots looks like that's 2. R2 is going to have 2 columns and 3 rows. 2, 3. Looks like that is 1, 2, 3, 4, 5, 6 total. R3 is going to be 1, 2, 3 by 1, 2, 3, 4. Total number of dots there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's see here. Not arithmetic, because we add 4, and then we add 6. Not geometric, because we multiply by 3 and then multiply by 2. But to get the number of dots in this array, think about it as like the area of a rectangle. It's just the number across the top multiplied by the number of rows. Well, if there's n columns and n plus 1 rows, then Rn every time will just be n times n plus 1. N across the top and n plus 1 rows. So that's a formula for Rn. Kind of cool. You can check it. R3 should be 3 times 4, which is 12. R2 should be 2 times 3, which is 6. R1, 1 times 2, which is 2. Nice. All right, that's all we have today. So I just wanted to share with you something I saw at Target. I actually saw this last year, and I have a kind of a collection of pictures that I like to keep that show bad math. So take a look at this picture and see if you can figure out what's wrong with it for yourself. Look at those prices. So this is a 2-pack. This is a 2-pack of contact solution. This is a 1-pack. So the 1-pack is $6.39. The 2-pack is $13.49. What's wrong with that? Shouldn't it be that when you buy 2, it's cheaper? But if you buy 2 of the singles, 2 of these singles I think would be what, like $12.78? So it's a better deal to buy 2 of the singles than the 2-pack. When I saw this, I got 4 of these. Because I was just like, why would I buy the 2-pack when I can get 2 of these for cheaper? So that is the wonders of Target just at work right here. Got a Throwback Thursday for you too. This is the Notre Dame football field. This is yours truly. And this was my senior year when I was drum major. And this was kind of my spot. And there was one of the piccolo players in the front row that said, I have to take a picture of you there because that's where you always are watching the game. I like to kind of be down at the level of the field because you could see in between the players and you could see what was happening with the ball before the snap. So this is your Throwback Thursday for the day. And I hope that you guys learned a little bit about arithmetic and geometric sequences today. Your homework is the Lesson Masters 8.1 and 8.2. Both of them are 2 pages, but I have great faith in you guys. You'll be just fine. I love you guys. That's why I'm here. Have a great day, and I will see you soon.